Microphone is muted. Good afternoon. Can you hear me?
Good afternoon, sir.
Okay.
Yes, sir.
Okay. My mic was muted. I was talking, so I did not notice my mic is muted. Anyway, so we will start the new topic today on jet engines. Okay. Let me just check. So I have uploaded the codes for the industrial gas turbine cycles. You can take a look at them. Means yesterday we had discussed these three codes. Means I have shown results by picking from these three codes. One is for real cycle, means just at a single point design point calculation. Then to draw the graphs for efficiency, you need to use this one, gas turbine real cycles comparison. If you don't remember, you can go back to the video and notice. Okay. Internet connection is very poor, it seems. I will connect back to the to my mobile. Can you hear me, students? This also has bad network
Yes, sir.
connection. Okay. Both connections are bad. Let us see. So this is recorded, so you don't need to remember this. So gas turbine real cycles is the design point calculation. Comparison is for the efficiency plots, and WNet is for the specific work output plots that I have shown yesterday. And you can correlate some of the results, try to understand by running the simulations. Although I have not put any comments, I have quickly written these codes. No comments are there. You can run and you will be able to understand. These are the old codes. Gas turbine cycles means 4 cycles without intercooling and the 4 cycles with intercooling. This already you have done. Okay. And let me check whether today's file has uploaded properly. (63, 64, 65, 66). Okay, it is correct. So before going into the written part, we'll go through some slides. We have gone through the slides once quickly, but I will just recap once again. Okay. So what we have done is we have discussed about industrial gas turbine cycles. We have not discussed about the individual components. We have done cycle level analysis. I hope you can still hear me and see the screen. Can just one final time, can somebody confirm? You can see the
Yes,
screen
sir.
and hear me? Okay.
Yes, sir.
So fine, thank you. So we have done cycle level analysis, different types of cycle level analysis for ideal cycles and real cycles, and you should run I suggest that you run some of these codes to understand how the efficiency impacts drastically the overall efficiency, means how the efficiency and losses of each component drastically impacts the overall efficiency. Means ideally if we could have obtained 60-65% efficiency, in real life we obtain 30-35% efficiency because of losses. Okay. So although ideally we could have obtained, means theoretically the efficiency should be much larger than steam turbine plants. In real life the efficiencies are of similar order. Okay. Why theoretically we could have obtained much larger efficiency as compared to steam turbine plants? Theoretically why we could have obtained this very large efficiency for gas turbines as compared to steam turbines? Anyone can answer? Actually, we don't get, but theoretically, we should have obtained much larger efficiency for gas turbine plants as compared to steam turbine plants. Means ideal cases. No answer? Sanjay, any answer?
No, sir.
Okay. So what is the temperature, maximum temperature of the steam cycles? Steam ultimately very difficult to operate at very high temperature, right? Maximum means steam reaches critical point at 300 something degrees centigrade, 372 or something. And you can superheat it, but ultimately even if for superheated cases also you will see that steam turbine plants maximum temperature that is reached in steam turbine plants is of the order of 600 degrees centigrade. Okay. Whereas for gas turbine plants, we can reach very high temperature. 12 means for the fluid, we can use 1200, 1300 degrees centigrade. It is only limited by the design of the means material of the blades. So if the maximum temperature or average temperature of heat addition is higher for any heat engine, you know from basic thermodynamics that the ideal efficiency should have been higher. Okay, because the temperature of heat addition is higher. In real life, because of losses, we are losing. So, but ideally, because the average temperature of heat addition is much higher for gas turbines as compared to steam turbines, we could have obtained much higher efficiency. Okay, but in are so drastically affecting the gas turbine and not the steam turbine. Means steam turbine also has losses, right? But ultimately, I am saying that both the efficiencies in real life are of similar order. It means that the real life losses in steam turbines are much less as compared to gas turbine plants. What can be a reason for that? Think about it.
So that fuel and all is actually not added in like steam turbine. It's just
No, not really, because here fuel is added, that is true. But there also heat addition is there, that is due to external combustion. Here it is internal combustion. Actually, with your logic,
Sir,
it
is
should have been
steam
even better for gas turbine. Means because steam turbine you are adding heat externally. There is some heat loss from external combustion to the heat addition to the working fluid. Here directly the working fluid is getting heated because of combustion. That is not the logic. So any losses in any components will contribute towards the overall losses in the cycle, right? So now there are turbines in both cases which may have similar isentropic efficiency. Whereas say pumps and compressor, if they have similar isentropic efficiency, what will happen to the overall cycle efficiency? What is the pump work input as compared to overall work output in a cycle in steam turbines?
very
What is
less?
the very less 1% or
very less.
less? Yes.
One,
What is the compressor work
1%.
input as What is the compressor work input as compared to overall work output or turbine work output in a gas
Around
turbine cycle?
half, I
Around
think.
half. So huge difference, right? So any losses in the compressor will significantly contribute, means drastically contribute. You can draw the graph towards the losses of the means towards lowering the overall cycle efficiency, and as a result, you get the overall cycle efficiency is reduced to much lower level for gas turbines. Okay, you have to think logically like this. This may not be mentioned in the books, but you can connect the dots. Okay. Anyway, so that part is finished. We will discuss about all the individual components like the centrifugal compressor for a couple of weeks later. For axial compressor, we will spend 1 or 2 weeks later. Okay, like blade design for both them. Centrifugal compressor is like a centrifugal pump, somewhat like a centrifugal pump. We have an impeller and diffuser. We will study these things in brief details and do some design calculation. And then axial compressor is more like a fan, like series of fans, and that also we will study in details. And then we will discuss about turbines at the end of the course to conclude the course. Okay. So before all these parts, the major part of this course is the jet engines. Okay, so we will start discussing the jet engines today. So jet engines already I have given you brief idea. You also know because this is very common. Means sorry, just a second. Okay. Uh, we know that jet engines are like very widely used for aircraft propulsion. Okay. So you already know the history also. I have discussed previously how jet engines were invented. I will quickly recap once. So initially, when the aircrafts were conceived in the early 20th century, the main propulsion mechanism was what? It was reciprocating engine. Okay. So at that time, automobiles were also recently invented. At that time, means just few years back, automobiles had been invented, and there was not much gap in invention of aircraft, means in design of aircrafts. So because automobiles already used this auto cycle, means petrol cycles Okay, so similar type of cycles were thought of for jet engines, but because the power requirement was high, it was thought that multiple cylinders will be used like this we have discussed, and the power from all the entire assembly was put to a shaft, and the shaft was used to rotate a large propeller. Okay, and this type of designs became very popular. It started with First World War and was improved and was at the peak. Means these reciprocating engines were at the peak during the first half of the Second World War. Okay, and gradually during the 1950s they declined. Some commercial aircrafts during the 1950s were also based on reciprocating engines. This is a reciprocating engine aircraft. Okay, it looks like normal aircraft, but there are propellers which are being rotated by reciprocating engines. Reciprocating engines are same IC engines basically. And you can see that this is a very old aircraft because the windows are square windows. Okay, and you might have you might know because why nowadays there are circular windows, because there was an accident and it was found that the crack propagation started from the corner of the square window because of stress concentration, and as a result all modern aircraft, means for last many years, have rounded windows, not square windows, so that there is no stress concentration. If you have seen those one series was there on aircraft crash investigation or something like that, National Geographic. Many of you might have seen. Okay, there are a lot of interesting points regarding this. You can understand, you can get a good understanding of why these crashes happen, what are the different important things for aircrafts. Okay, Nat Geo series, aircraft air crash investigation or something like that. A lot of episodes are there, 50, 60 episodes are there. So one episode has dealt with this case. Okay, there are other interesting episodes. One in which the entire aircraft roof, one part of it blew up. However, the pilot was very experienced and could land the aircraft. In that, only one air hostess who was not strapped actually flew out of the airplane. Everybody else was like having their seatbelts on. So nobody, although the total roof was open, nobody flew out of the aircraft. And in that condition, the pilot managed to land the aircraft. So a lot of interesting episodes are there. I'm digressing. Another very interesting episode is there where the front window, because of some design flaw, the front window blew up. And so there are two pilots generally, right? For normal aircraft, two or three pilots. So two pilots or a flight engineer. So the main captain and the what is the other person known as? Means
Co-pilot.
captain, pilot, right? So the co-pilot or the captain, one of them actually flew out of the front window. Okay, but the engineer, flight engineer, and the other pilot managed to. One of them managed to hold him. There was third person, the flight engineer. Old days there used to be three persons in the cockpit for large aircraft. One flight engineer used to be there who used to monitor all the different data from like all the signals from the different sensors, and so he managed to hold the feet of the pilot who flew out of the window. So the entire upper part of the body of the pilot was outside, and only the legs were inside. And somehow that person managed to hold him very tight. And in that condition, and it was at very high altitude, means minus 30-40 degree. I forgot. The other pilot managed to land the aircraft, and miraculously, actually, that pilot who flew out of the window survived this accident, and nobody actually died in that accident. So a lot of interesting episodes are there. You can see. Sometimes it can scare you when you are actually trekking an aircraft. So might not be suitable for all the students. So small vibrations in an aircraft also, you may feel that, oh, it's like that aircraft that I have seen in that episode, and something is wrong. But otherwise, it's a very good series. So anyway, let us come back to this. Yeah. So initial aircrafts were reciprocating engine based. The other mode of propulsion in air, okay, at that time already it was conceived, was what? Was rocket propulsion, that we already know. So rockets were already conceived at that time. Okay, rockets are very, like, even from ancient times also Chinese people have discovered rockets, but like during the earlier 20th century, proper rockets were designed. So Rockets are not used for aircraft, but it was conceived that it can be used. So what is the main conceptually? What is the main difference between rockets and jet engines, and what are the advantages and disadvantages of using rockets as compared to jet engines? Very simple question. What is the main conceptual difference between rockets and jet engines, and what is the advantage of using rocket, and what is the disadvantage of using rocket, or other way around, what is the advantage of using jet engine and what is the disadvantage of using jet engine?
Sir, in rockets we can get thrust very fast. In jet engines, it actually takes a lot of time to get that.
That is true, but that is not the main that is a side effect or after effect. Yes, fuel.
Fuel, then for different cases, we use different kind of fuel, rocket and jet engine.
It is only for efficiency. Rocket can also use similar type of fuel. You are somewhat close. Main difference is that rocket also carry the oxidizer with it. Okay,
Yes.
not only the fuel.
Oxidizer, yes, sir.
Oxidizer.
Higher altitude, yes, sir.
Yes, the oxygen also is carried with it. So fuel can be hydrogen or anything, but the oxygen is also carried, so it does not need an atmosphere to fly. Means in atmosphere also obviously it can fly, but outside atmosphere also it can fly. So it can reach very high altitude, or say in space it can go. So jet engines are air breathing engines, where the fuel is carried by the jet aircraft, but oxidizer is not carried for the combustion. Oxidizer needs to be taken all the time, like the air is taken. Air is basically the oxidizer because it contains oxygen. So it is taken from the atmosphere. So this is the conceptual difference, main difference. So now what is the main advantage then in using jet engines as compared to rocket engines? The weight of the rocket engines, the weight ratio is very poor. What I mean by the weight ratio means that for
Thrust to
supply,
it.
yes, if you want to take, not thrust to weight, okay, if you want to take a payload, rockets are very high thrust. The main thing is that, say if you want to take a payload of 100 kg, the mass of the fuel and oxidizer becomes very large as compared to the payload mass. Means the most of the mass of the rocket is being just taken by the fuel and the oxidizer, and it's like a cumulative effect. Means now if you want to carry more fuel, you will need even more fuel and oxidizer because mass is even increasing. Okay, so that's why it becomes very complicated. So you will notice that if you read about rocket engines like spacecraft, that the payload is very small as compared to the actual fuel tanks that are carried and rejected after some altitude. The fuel tank may be 10 times or even more, has even more mass. Payload is a very small, insignificant mass as compared to the fuel and oxygen. So jet engines, on the other hand, are very lightweight because it needs to only carry the fuel. It means jet engine plus the fuel, total assembly is much lighter as compared to a rocket engine plus fuel plus oxidizer. So that is the main advantage of using jet engine. What is the main disadvantage? Obviously, it cannot fly at very high altitude. Means there is a upper limit, upper ceiling. If the atmosphere becomes very thin, you cannot use a jet engine. Okay. So because it needs oxidizer, so it cannot fly at like say at the border of say at 30-kilometer altitude or something like that. So maximum upper limit that is reached is around 20-25 kilometer with specialized military aircrafts. Okay, for jet engines. Commercial aircraft fly at around 10 to 12 9 to 12 kilometer altitude, around 10, approximately around 10 kilometer, 10 to 12 kilometer altitude. You will see that the pilot announces that we are flying at 38,000 feet, which is around 12 kilometer, 11, 12 kilometer. So that is the main difference. Okay. So rockets were already there, but because of that drawback, something needed to come up. Some design needed to come up. Okay. And reciprocating engines were good, but reciprocating engines were very complicated. Okay. Because you have so many, you are ultimately converting a reciprocating motion into a rotary motion in a reciprocating engine. So there is always some chance of unbalance. Then other types of, like, if you are not properly designing, then there is there are a lot of problems and also reliable, like flow of lubricant because of centrifugal forces. All these things were there. Efficiency also was not. So during the Second World War, just before the Second World War, we have discussed already, and you can even read. You must know already. This is very common quiz question that two engineers, one from UK, Frank Whittle, and one from Germany, von Owen, came up with the idea of jet engines, jet engines means gas turbine based engines for aircraft propulsion. Gas turbines at that time were not popular, but steam turbines were already there. Okay, so they came up with the idea of gas turbines for aircraft propulsion instead of reciprocating engines, and quickly it became popular. And the von Owen design was what actually became more popular. The Frank Whittle design was slightly different. He used a centrifugal compressor, so he had a large cross-sectional area. Centrifugal compressors have large cross-sectional area, so the drag was larger. At that time, it was okay, but nowadays this type of designs are not used at all. But the von Owen engine, German design, was with an axial compressor, so it has a smaller cross-sectional area, so smaller drag, and it became very popular gradually. So this first set of engines were known as turbojet engines. Okay, so we are going to start with the turbojet engines, and then we will go into analysis of turbofan, which evolved after a couple of decades, and then turboprop, which also evolved, but are used to have a different set of applications at low speed applications. Okay, and then we will. So these three are the main aircraft engines which are still being used nowadays. Turbojet is used for military aircrafts, turbofan for civilian aircraft, most civilian aircrafts, and short distance civilian aircraft use turboprops. Then we have ramjets, scramjets, which have been developed at a prototype and experimental stage. Ramjets are used widely for missiles, cruise missiles, but not for manned aircraft. Okay. Ramjets have a problem we have discussed, that it cannot start on its own. It needs some rocket or some mechanism to start. Okay, and then which is not used at all. It was conceived initially very early, but there are big design flaws and it cannot be sustained for long duration. Within half an hour, 1 hour, the engine fails. Okay, because of the failure of the valves. So recently again people have started to revive that pulse jet engine. We will discuss later without using valves. So there are some valveless design using acoustics, like without using valves, they try to stop the flow using acoustics. Anyway, let us come back to this turbojet. One by one we will go. So is the simplest type of missile. What we have, you already know, because we have studied about industrial gas turbines, we already know. So you have air coming in at high velocity. Okay, with increasing cross-sectional area, if the aircraft is flowing at subsonic speed. Okay, if it is if it is at a supersonic speed, then you need a convergent divergent diffuser. Okay, so diffuser main function is to reduce the speed and increase the pressure. Okay, so some increase of pressure already occurs in the diffuser, and that actually helps us in reducing the number of compressor stages. Then there are a large number of compressor stages, maybe 8 to 10, even larger number of compressor stages. Each stage is like a fan. Okay, you can imagine that ceiling fan you have, it is almost similar to that. Mechanism also is similar. You provide some power to the fan. Similarly, here also you provide the power. You are rotating it, and it is just forcing the flow from one side to the other side. Okay, and in the fan, the pressure difference from one side of the fan to the other side is very small because of the design of the blades. Here the blades are more angled, so you get more pressure rise as compared to the fan, and the number of blades are also more, so you get more pressure rise as compared to the fan. Okay, so gradually pressure increases and you have high pressure air at the inlet of the combustion chamber. This is like industrial gas turbine. Then combustion occurs with injection of fuel. All these parts, remember, we will study later. Means combustion chamber also separately in details we will study. Then you have a few number of turbine stages. The number of turbine stages here are less as compared to industrial turbines because you need just enough power to run the compressor. You don't need any extra power. So it just extracts enough power from the fluid, hot fluid, to run the compressor stages, and rest of the fluid still has quite a bit of enthalpy. I mean, it is not reduced to very low temperature and pressure. Means the pressure remains still high as compared to atmospheric pressure. So then there is pressure drop in the nozzle up to the atmospheric, and you get accelerated flow outside. So ultimate aim was to just generate thrust, which means that flow has to be accelerated at the outside. Now we can use rocket to accelerate the flow to the outside or jet engine. So in this case, we are using air breathing jet engines to gas turbines to accelerate the flow to the outside. Okay, so that is the thing. Why do we need this compressor and turbine for like if there was no diffuser, we will need compressor and turbine, right? So why is it needed for accelerating the flow? Why don't we just, because if air is anyway coming, why don't we just combust it with fuel and then pass it through a nozzle?
Sir, residence time might be very low.
What will be low?
Like the residence time of the, we won't have enough time to burn.
Let us consider that we can slow down the flow through baffles and other designs. That is not the reason. Will it generate any thrust? Can we accelerate the flow in the nozzle at the intake, because there is no diffuser? We ignoring the effect of diffuser. Flow is coming at atmospheric pressure. Even if you combust it, it is open at both sides, like a combustion occurring in an open pipe. So after combustion, the pressure does not change. It's not like IC engine. Okay, any of the combustion chambers here, the combustion process is constant pressure combustion. Okay, like a large flow area is there where the combustion is continuously occurring. So if there is no pressure rise, so at the inlet of the nozzle also pressure is atmospheric pressure, at the outlet of the nozzle also pressure is atmospheric. So the flow cannot be accelerated in the nozzle at all because there is no pressure difference. So pressure needs to be increased to accelerate the flow in the nozzle. Okay. Now there are two ways to increase the pressure. One is to use a compressor, and if the velocity is very high, like in ramjet engine, we can take away the compressor. Still, we can compress by using the diffuser. Okay, but for all normal cases, we need the compressor to compress to increase the pressure because otherwise we cannot expand the fluid in the nozzle. Means there cannot be a pressure difference across the nozzle unless there is high before the nozzle, and that's why compressor is needed. And then you need the turbine to run the compressor. Role of the turbine is to run the compressor. Okay, and if you don't have any combustion process, the amount of turbine work input will become exactly equal to the amount of compressor work output, means if only you take the pressure again back to atmospheric pressure, so you will not have any extra energy left in the fluid to extract in the nozzle. So you need the combustion process so that the compression line is shift from the expansion line. Okay, so for example, if you do not, I will come back to this anyway. If you do not have say ideal case, okay, there is a compression process. If there is no combustion, again you come back through the same line for the turbine expansion. So compressor and turbine work becomes equal for the same pressure rise. So you can get any expansion in the nozzle. So this heat addition in the combustion chamber is also needed. Okay. These are some fundamentals you should be clear about. Okay. So anyway, let us come back to this. So this was the design. Okay, and the other design using centrifugal compressor also is similar, but only thing is that the footprint of the centrifugal compressor is different. Centrifugal compressor, you have flow coming in axially but going out radially, and then it has to be turned in the axial direction again. So as a result, the length is shorter, but the radius is larger of this engine, and the larger radius means it's very detrimental because it increases the drag of the aircraft, which we don't want. The drag is one of the most important criteria of aircraft, reducing the drag. Okay, so you don't want the drag to increase. So as a result, this type of design is not used. This axial type of design is used for turbojet. Okay, so this is the simple thing. We will discuss later what is the difference in turbofan engine when we go back to turbofan. So the couple of drawbacks why turbojets are not used now. Anyway, we will discuss once we discuss turbofans, but I will mention here once. Okay, one is that turbojets are highly efficient at very high velocity, means Mach 2 around that velocity, means much higher, means than sonic velocity. At supersonic velocity, they are efficient. But at low velocity, turbojets are not. So when I mean efficient, we will see in the next class that there are two types of efficiency for aircraft. One is the efficiency that you already know, like how efficiently the fuel, the energy is getting converted to shaft work. Okay, or that part of efficiency, like that we already know, cycle efficiency. But there is another efficiency called propulsive efficiency, which actually tells us how much of the kinetic energy that is being carried by the exhaust gases is actually wasted. Okay, and for turbojets, the exhaust gases go out at very high velocity as compared to other type of thing. And if the exhaust gases go out with very high, the amount of kinetic energy of the exhaust gases is also very high, and lot of energy is actually wasted. This we will discuss in detail after discussing turbofan engine. Okay, what is the actual thing? You might say that, but we need high velocity for generating thrust. Okay, that is not true. We need high change of momentum, means mass into velocity. Even with smaller change in velocity, if we increase the mass flow rate, we can get large amount of thrust. Okay, and that actually leads to less loss of kinetic energy, as we will. Okay. So anyway, so this was one of the main drawbacks. That's why for military aircraft we still use turbojets, because they fly at very high speed. Civilian aircrafts are not flown at those kind of high speeds. They flow just below the sonic speed at Mach 0.9 or Mach 0.85 is the cruise speed for large aircrafts. Small aircrafts fly at lower, so they use turbofans. And the second main problem for turbojets, because the exhaust gas goes out at very high velocity, they create huge turbulence and huge amount of noise. Okay, you guys are not familiar, because I am guessing that most of you have traveled by aircrafts. Okay, nowadays it has become so common. But the aircrafts you are traveling are quite it is not pleasant. I cannot say it is pleasant because the seats are cramped, but sound wise it is pleasant because there is not much noise. But during the 1980s, because I have traveled at that time during 1980s, during my early childhood, the aircrafts used to be very noisy, means very noisy. You cannot imagine how noisy. Like something is everybody used to have earmuffs, large headphones like struck, means earmuffs. So instead of headphones, you can imagine that a large over the head headphone is present, which is like a earmuff. Okay, everybody used to have, actually aircrafts used to provide earmuffs, large earmuffs to all the passengers. Otherwise, you cannot sustain. You will vomit. That was so much noise was there. It was very unpleasant in that way. Other things were good, large food space and good food, but that was one of the main drawbacks of turbojets. So turbofan actually reduced that noise drastically. So this was a big drawback, turbojet engines. Okay, and then when we are talking about efficiency, we know that efficiency is good at high speed for turbojet, but generally civilian aircrafts, by regulation, you should not fly at very high speed, means supersonic speed, because near the civilian places, like if you break the sound barrier, there is a large sonic boom. That means it can be very distracting, or means quite bad actually, that sonic boom. Okay, sometimes people get confused confuse it with explosion. Recently, one incident was there in Bangalore, where one aircraft actually near the civilian area where it was not supposed to go supersonic. It went supersonic. It created big sonic boom, which was heard from entire Bangalore. So that is so that's why turbojets also near city airports, it is not possible to fly. Still, people have used supersonic aircraft like Concorde, which was a very prestigious aircraft, as you know, but it used to fly subsonic until it left the land area, and once it was over the ocean, then it used to break the sound barrier and used to fly at supersonic speed. And the speed was very high, Mach 2. Means you can imagine nowadays it takes so much time to fly, say London to New York, but it was more than twice faster in old days if you could afford to fly in Concorde. You might have seen a few documentaries, very interesting. Okay. Turbojets were used for Concorde. So let us, and so this is just a basic introduction that I am giving, with some historical background and some interesting stuff. We will come back to our mathematics again. Okay. And again, remember that this part is overall calculations. Later we will go through individual components separately, combustion chamber, things like that. Any questions up to this point?
No, sir.
Okay. Let us carry on. Actually, I am not even discussed any technical aspect. I am just giving some interesting insight. So I have just written here all these things what we have discussed. The main jet propulsion cycles are turbojet, turbofan, turboprop. I hope you can see the screen. I will enlarge it. Turboprop, ramjet, scramjet, pulse jet. Other types of aircraft propulsion devices can be reciprocating engines or rockets. Okay, which are both of them are not used. So we will start our discussion today with the turbojet engine. Okay. So when we draw the schematic of the turbojet, we draw it like that. My diagram has become a little bit elongated, but otherwise it is the way to draw. You have a diffuser section like this, which is shown like this. Opposite of a nozzle, the area is increasing. Then you have the compressor. You already know how to schematically draw the compressor. Then combustion chamber is not exactly shown in the design, but we know that within this cavity there is combustion chamber. Multiple combustion chambers are present around the periphery. Then we have one or two turbine. Generally, one turbine will be there. Means one turbine means it has lot of stages, but the overall the turbine is one turbine. In some aircraft there, and then you have the nozzle. Okay, and if it is a military aircraft, after the turbine, there can be a long section which is known as the afterburner, which will also. Those of you who have seen the engine that is kept at in our lobby, MiG-21 engine kept in our lobby, also can must have taken a look at it. That is also turbojet engine with afterburner. The other new students, once you get a chance to come back to the campus, you can take a good look at the engine, and you can even rotate the engine and see. Means if you rotate the turbine blades, you will see that. If you rotate the compressor blades, you will see that the turbine blades are also rotating on the other side, because all of them are coupled on the same shaft. And then there is a long afterburner section, almost like 3-4 meters long. The afterburner itself, with lot of fuel injectors, all these things you can see. It is kept in our SMS lobby. For the new students, I am saying this. And I have also made a chart showing all the different aspects of this, and it is shown as a poster in the so where I have shown the different parts of this MiG-21 engine and the basic cycles for common people, means though not for students or us who already know all these things, but for common people we have developed a chart and put it on the lobby. You can take a look when you come back. So let us come back to this. So now we will take a look at the processes that are happening. Okay, processes. Now we will take a look with actual processes. There is no point in studying ideal cycles anymore. Already we have studied a lot of ideal cycles, but in real life everything is non. So we will start with actual cycles. Can you still see the text, right? You can see that. So the atmospheric condition outside, I should have written, is denoted. Say it is denoted by A. A is the atmospheric condition, static condition at the atmosphere. Static condition means static temperature, static pressure. So I will denote static temperature by TA, static pressure by PA. Okay, and velocity is VA. So what is the stagnation condition of? We will denote it by T0A and P0A, which is the standard notation, right? Static condition TA, stagnation condition T0A, P0A. What is the relation between TA and T0A?
0 is equal to
Anyone?
plus e square by cp. Sir,
Yes,
t
divided by 2c.
0
Okay. TA is equal to T0 is equal to TA plus VA square. VA is the velocity. VA square by 2. And you can easily calculate, derive this from enthalpy. So
yes, sir.
basically enthalpy, first law equation gives us that H0 is equal to HA plus half VA square. From that, this relation comes. This is very already known. We have discussed also for real cycles. Okay. So T0 is the stagnation condition corresponding to the static condition A. Okay. Outside the diffuser. So what happens in the diffuser? Instead of following the ideal path, there is always always all the lines will deviate towards the right hand side because entropy is increasing in real life, right? So there are some frictional losses, and entropy increases. So what will happen if there are frictional losses? What will happen to the pressure? Means without any losses, if it was the ideal, the pressure would have increased. If I can reduce the velocity VA to 0, pressure would have increased to P0A and temperature would have increased to T0A. If I could reduce the velocity to 0 at the end of the diffuser. Obviously, you cannot make it 0, but if you can make it negligible, pressure would become P0 and temperature T0A. Correct? Or is there any confusion? I'm going very slowly. This diffuser part actually confuses every year a lot of students. That's why we have to be careful. You have to be careful in this area. Okay. So, at the end of the, yes, tell me.
Sir, the initial point which is A denoted by in this graph, sir.
Yes.
And what is that point defining? Air at static condition or air is
Point A is outside the engine, just outside the engine at static condition.
means
Means the temperature.
When the flight is stopped.
No, flight is moving forward at velocity VA.
Okay.
So from the point of view of the flight aircraft engine, the air is coming in at velocity VA. The static temperature for a flow you don't know. Means,
yes, sir, no, but I have to consider stagnation properties, no, sir, because it is.
yes, correct. But let us start with the static property. Static temperature is TA, static pressure is PA, and velocity is VA. What is the stagnation property here outside? What is the stagnation temperature?
T0, you said that.
T0A, correct? T0A. Okay. So what happens in an ideal diffuser or an ideal nozzle to the stagnation temperature and stagnation enthalpy?
Isentropically increase.
Say it's the isentropic process. If it is an isentropic process in the diffuser or nozzle, now this diffuser is just the opposite of a nozzle. So you can think about a nozzle. What happens to the stagnation enthalpy in a nozzle for an ideal case, isentropic case? Stagnation enthalpy increases, decreases, or remains same. What happens?
Increases.
Why stagnation enthalpy will increase? What does it mean, stagnation enthalpy? Energy is increasing. Where from this extra energy is coming?
Kinetic energy to this potential.
Kinetic energy is already included in stagnation enthalpy. Fundamentals need to be strong. It remains constant, right? We have studied it also, but we don't need to study this. This is common sense. Let me just go back to what we had discussed. Where is that? 7. Huh? What does the first law? You have forgotten, everyone. Huh? First law, thermodynamics, fundamental thing. Job interview, you have to tell the first law, right? Everybody knows the first law. First law tells us that for a steady state steady flow process, H1 enthalpy plus half V1 square plus heat input is equal to H2 plus half V2 square plus work output. if there is no change in potential energy. So if there is no heat input or work output in a nozzle, is there any heat input?
No.
Is there any work output? No moving part, no work output. Okay, without moving part, work output cannot be there. So for a nozzle, what is the equation? First law equation, energy balance. H1 plus V, half V1 square is equal to H2 plus half V2 square, correct?
Yes.
So static enthalpy, what happens in a nozzle to the velocity? Velocity increases or decreases? Increases. So if H1 plus half V1 square is equal to H2 plus half V2, if V2 is greater than V1, what happens to H2?
It's becoming less than H1.
H2 is less than H1. Now what happens to stagnation enthalpy? What is the definition of stagnation enthalpy? Can you write this first law equation in terms of stagnation enthalpy? I have
It
already
brought to rest.
written here.
The enthalpy generated when it was brought to rest isentropically, so it becomes constant.
So H1 plus half V1 square is equal to H01. So in a nozzle or diffuser, H01 is equal to H02, right? Because Q and W are 0, right? Is it clear to everyone? This is very fundamental. In a nozzle or diffuser, Q and W are 0. No heat input, no work output, no moving part. Basically, just flow is off. So H1 plus half V1 square is equal to H2 plus half V2 square. This is basic thermodynamics. And H1 plus half V1 square we can write as H01. H2 plus half V2 square we can write as H02. So H01 is equal to H02. So no change in stagnation enthalpy occurs in a nozzle or a diffuser. Okay. Physically, it means that the energy of the fluid does not change in a nozzle or a diffuser. Energy is only converted from enthalpy to kinetic energy or kinetic energy to enthalpy. Static enthalpy means internal energy is increased, but there is no change in overall energy of the fluid that is going through a nozzle. Because how can overall energy change? Because I am not supplying any energy and I am also not extracting any energy out of this. It is just flowing, and if there is no friction, there cannot be any overall change. Okay, is this clear? This point to everyone? Very important. Without this, all problems will be wrong. Fundamental thermodynamics. Okay, second year you have studied in BTech. So let us come back to our discussion here. So if it was an ideal diffuser, what would have been the stagnation enthalpy at the end of the diffuser?
Same as in
Initial. So what would have happened to the
HA plus
stagnation
half.
temperature? What? HA plus half V1 V square, correct? So what will be the stagnation temperature before the diffuser and after the diffuser? If it is ideal diffuser, isentropic diffuser, stagnation temperature.
It will be same, right? Because stagnation enthalpy is same.
Correct. Same. So you don't hesitate. Tell me that it will be same. Because there is no change. Stagnation enthalpy same means stagnation temperature also same. Because enthalpy temperature is just related by H is equal to CPT. Right? Whether it is static, stagnation does not matter. So because stagnation enthalpy is same, stagnation temperature will also remain same in ideal case. Okay. So at the inlet also stagnation temperature is T0A, and after the diffuser also ideally it should have been T0A. Okay. What about the static temperature at the end of the diffuser in ideal if the velocity is brought to 0?
Increase.
What will be the value? Static temperature TA equal to?
Plus V square by 2.
Not TA equal to. TA plus V square, VS square by 2CP at the end. Means static temperature will become equal to stagnation temperature because you are bringing the velocity to 0 isentropically. Correct? So now if there are frictional losses, so before going to that, what will happen to the pressure at the inlet? The stagnation pressure say P0. What will be the stagnation pressure at the outlet if it is an isentropic diffuser?
Pressure should decrease. No, sir.
Why will it decrease?
Increase, sir. Sorry.
Stagnation pressure. Why will it increase?
Sir, it will stay same if it's isentropic, right?
Correct. It will stay same, right? Because what is the relation in an isentropic process? T2 by T1 is P2 by P1 is equal to T2 to the power gamma minus 1 by. Correct. So now at the initial point also stagnation temperature is T. At the final point of the diffuser also stagnation temperature is T0A. Is this clear to everyone? That there is no change in stagnation temperature in the ideal diffuser, or is there still confusion? So if the stagnation temperature remains same, so T0A by T0A to the power gamma by gamma minus 1. So from this you get that stagnation pressure also should remain same.
So ratio become
Or
1.
is there any confusion still now? Yes?
So ratio become 1. Sir.
Yes. So initial stagnation pressure and final stagnation pressure after an ideal diffuser, isentropic diffuser should. What about the static pressure? Initially it was PA, atmospheric pressure. What will happen to the static pressure? How will you calculate the static pressure if it is ideal at the end of the diffuser?
Using that adiabatic equation, isentropic equation, gamma relation.
Correct. So what will be the value? Yes. What will be the value? Because we know that P0A means at the end, whatever is the P, that value by PA should be equal to T0A by TA. Okay, static temperature has changed from TA to T0A. So to the power gamma by gamma minus 1. So from that we get that static pressure at the end also should become equal to P0A. If there are no mist will become equal to stagnation pressure, because we are isentropically bringing the fluid to zero velocity. And you understand that if you isentropically bring the fluid velocity to zero, the static pressure becomes equal to stagnation pressure. Is this clear up to this point to everyone?
Yes, sir.
Okay. Does anyone have any class after this, or can we continue for a few minutes? This concept is very important. I want to just finish this part.
Yes, sir. Continue, sir.
Anyone with any class? No, sir. Means no for you, but others have classes. BTech fourth year. BTech dual degree fifth year. Yeah. MTech no classes. Okay. PhD students are not there, right? In this course. So now this is the ideal case. Okay. What will happen if there are frictional losses? Means non-ideal case. What will happen to the stagnation enthalpy in a nozzle if there are frictional losses? We will come to diffuser first, but nozzle is easier to understand. So if there are frictional losses in the nozzle, within the nozzle, but outside it is still adiabatic, what will be the change in stagnation enthalpy in the nozzle? Will there be any change in stagnation enthalpy?
Yes, sir. It can reduce.
Increase the
Suppose it is reduced, right? Suppose it is reduced because of frictional losses. So where will this extra energy? Because initially the energy was H0A. Now say it has reduced from H0A to 90% of H0A. So where does this 10% energy gone from friction?
Some heat dissipation or
Frictional
something.
loss, heat dissipation, correct? So if it is a insulated thing, if we consider that the thing is insulated, how will this heat dissipation manifest itself? It will contribute to the temperature itself of the fluid, right? So actually temperature still means energy is still balanced even if there is friction. Okay, even if there is friction, the enthalpy is still balanced. Stagnation enthalpy does not change. Okay. What will change in that case if there are friction, or say you have a flow through a pipe? Okay, you have a flow through a pipe and there is huge frictional loss in the pipe. What I am saying is that flow from one side of the other side to the other side of the enthalpy, stagnation enthalpy does not change. Okay, stagnation enthalpy still remains same. What will change if there is huge frictional loss?
Temperature, sir.
Pressure.
Pressure loss.
Temperature cannot change.
Pressure loss.
What I am saying, because frictional loss itself is again contributing back to temperature. Whatever energy is lost again is manifested as temperature. Temperature cannot change. Pressure loss will be there, right? Right. So there will be pressure loss because of friction. Okay. So what happens in a diffuser? Today we will just discuss the diffuser part. All the other parts you already know, and we will continue our discussion. But this part is again I have drawn in a actually it's supposed to be magnified. It's almost same scale, but just focusing on the diffuser. Okay. Ideal process should have gone from A to 0A. Okay. Where the temperature should have increased from TA to T0A and pressure should have increased from PA to P0A. But because of frictional losses, we follow this path, green path, instead of the blue path. Blue path is supposed to be the ideal case. We follow the green path. Okay. But because the final enthalpy and temperature remains same, because even for with frictional losses, we still reach the same temperature. Okay. So the point where we reach the same temperature and we like the change on if entropy that happens due to frictional losses, at that point whatever is the pressure is the new pressure at that point. Okay, and this pressure is lower than the ideal pressure that could have been obtained. Ideal pressure that we could have obtained if it was an isentropic diffuser was P0A, but because we are deviating to the right side, instead of P0A we reach P01. Okay, the pressure becomes equal to P01. Remember, the velocity is becoming negligible. So at this point it is static and stagnation pressures are almost similar. So actually stagnation pressure is reduced and static pressure also. So it is reduced. So instead of P0A, stagnation pressure actually is becoming P01. Okay, because of frictional losses. But stagnation temperature and enthalpy still remains same. T0A is equal to T0. Is this point clear to everyone? This is where actually most of the mistakes. So people think that we will only go up to a lower value of temperature, but in actual case for the diffuser we will go to the same value of temperature, but the pressure will decrease. Okay, but the students either what they do is they go to the same value of pressure, continuing this line here like a compressor, or they just assume that temperature decreases. In the compressor, how it looks like, compressor is different as compared to diffuser. See the compressor, the green line finishes at a higher temperature as compared to the blue line. How is it possible that despite losses temperature has increased in the compressor as compared to ideal case, but not in the diffuser? All these are very fundamental things you should logically think instead of memorizing. In the diffuser, our stagnation temperature could not increase even if it or could not did not decrease even if there is lot of friction. It's remains same because I have said that frictional losses manifest as temperature, because ultimately frictional losses are what? It generates heat. So heat will again contribute to temperature. So then in that case, in the compressor, ideal case the temperature is lower, but actual case temperature is higher, means enthalpy also is higher. In the actual case, H02 is higher than H02. Why is it possible in the compressor?
Sir, we are giving more work input, so
Correct,
that
correct.
work heats the fluid.
Yes, yes. We need to give more work input, but in the diffuser we are not giving any work. Okay, here we are giving more work input, so that's why we get more temperature. It's possible. Okay, but in the diffuser it's not possible. You will reach the same temperature always, even if there is loss. So what will happen if there are more losses? If you have a very poor quality, say instead of German-made nozzle, you have taken a China-made nozzle. Okay, although Chinese people are also making very good quality, but I'm just making fun here. But so it will deviate more towards the right hand side like this, correct? But ultimately, what will be the final temperature? It will be same as this temperature. So it will be somewhere around here. If you can see my cursor, it is at the same height, same temperature, but on the right hand side of 0. So what will happen? The pressure loss will be more. Means the pressure will be further reduced because the constant pressure line going through this point is lower than P01, but the temperature would have been same. So even if more losses are there, still temperature would remain same, but the pressure will keep on decreasing. Means the pressure that we can achieve, and that is not good for us. We want maximum pressure out of the diffuser. Why? Because
Compressor
then we
work will
need
be
less
decreased.
number of compressors. Correct. So if we have better quality of diffuser, we get as near to P0A as possible. And in the ideal situation, this 01 will coincide with 0A and P01 will become P0A. Okay. So, okay, let us stop here and let you guys just absorb this part, and because otherwise we have to go through a lot of discussion on how the efficiency is defined. So this diffuser efficiency is a very tricky concept. Okay, it is defined in a very roundabout way. It is not as easy as turbine or compressor. Okay, and that we will discuss in the next. It's defined in two ways, and it's very tricky. And there actually most of the mistakes occur because in terms of temperature directly you cannot define T01 by T01 minus TA by T0A minus TA because it will always become 1. So it is defined in a roundabout way for the diffuser. Okay, using some hypothetical temperature to 01S, which is not anywhere related to real temperature of the process. So that we will discuss in the next class. Let us stop here. If there are any questions, you can ask me. Okay, this diffuser part and the nozzle parts are very important. Once we go to convergent nozzle and choking, you have to be very careful with these two parts. Other parts, you know, it's very easy calculation. Enthalpy of the compressor, turbine, combustion chamber. Only the diffuser and nozzle parts become very tricky. So that we have to be very careful. Okay. So we will discuss the diffuser in details in the next class. So let me take the attendance. Meanwhile, if you have any questions, you can ask me. Material is already uploaded in the file section. Codes from the previous class are also uploaded. I strongly suggest that everyone downloads the code and try to run them in MATLAB and try to see different variation of different losses, what happens, things like to try to get a better understanding. And video lectures I have to upload. It takes a lot of time to upload the videos. So during the weekend I will try to upload. So let me see. What is the date today? 22. 22. Bharatram, present. Sachin Kumar Singh, present.
Sir. Yes, sir.
Sanjay,
Yes, sir.
Abhishek Anand. Abhishek, are you there? Abhishek is absent. Then Vikas present. Manthan.
Yes, sir. Present.
Yeah, Manthan present.
Present,
Ajay, where are you, Ajay? I cannot see Ajay. Ajay is absent. Gaurav is present.
Present,
Gaurav
sir.
is present.
Sir,
Yes,
present,
thank you.
sir.
Then
Hello?
who
Sir,
is
Gaurav, sir,
present?
present, sir.
Jishnu is present. Gaurav Khandelwal I was asking.
Okay,
I'm
sir.
going through
Yes,
roll
sir,
number.
Gaurav
Okay.
Khandelwal, sir, present,
Not. I've seen you are present. Okay. Jishnu is present. Then Suresh Kumar. Raparthi Suresh Kumar. I don't see Suresh Kumar. Okay. Ujjwal is present. Shubham Kumar present. Pushpendu. Shyam Kumar
Yes, sir.
present. Prabhat Kumar Mishra.
Yes, sir.
Present. Yes. Kishan Sai present.
Yes, sir.
Dhruv. Why this fellow is always absent? Anyone knows what has happened with him after the exam?
So
He is not attending. He has already left, or what happened?
Maybe he's leaving MTech, taking decision maybe.
Okay. Then Venkata Rajendra, present. Atul Jyotish, present. Atul is present, correct. Ramcharan, Suman is Ashwini Kumar, where are you? Present. Gaurav Srivastava present. Gulshan Kumar present. M. Pujari present. Pujari is present. Nilesh Kumar.
Yes, sir.
Where are you, Nilesh? You are present. Yes. Chintu present.
Present, sir.
Sudipto present. Lokesh Sonkar. Lokesh absent. Ankit Soni. Ankit absent. Shivangsh Das. Shivangsh is there. I will repeat again. Okay. Bharatram was present. Correct. Abhishek Anand is absent. Then Ajay Kumar Meena absent. Then Raparthi Suresh Kumar.
He's present, sir.
Presence.
Where is
Suresh.
Suresh Kumar or Ajay? Suresh Kumar is present.
Sir, I am present.
Okay. Suresh is present. Ajay Kumar is absent. Huh? Then Dhruv Garg is absent. Lokesh Sonkar. Lokesh is present. Huh? What happened? You did not respond. Parallelly watching movie. Huh? Ankit Soni. Ankit, I cannot see. Ankit is absent. So, okay, we'll meet in the next class Tuesday. Happy Dasera for all of you. Okay, we'll stop recording.